How do we know what's happening beneath a volcano, miles underground, where we can't see or touch? Volcanoes are unpredictable, but scientists have a secret weapon to figure them out: geophysics. Using sound waves, ground motion, changes in chemistry, and even satellite data, they can listen to and watch volcanoes from the inside out. Geophysical tools help us understand the hidden processes inside volcanoes. They're used by volcano observatories across the US, with scientists monitoring volcanic activity in real time, all to keep people and communities safe. Let's start by looking at what makes volcanoes so complex, and why they need such powerful tools to study them. Magma is created deep in the earth, where some rocks are melted from the high temperature and pressure there. This makes magma less dense than the surrounding solid rock. This density difference allows the magma to ascend through a volcano's pipes and conduits to the surface. Along the way, it may pool in magma chambers where it crystallizes or builds in pressure. Not all volcanoes erupt in a big boom like that, though. Whether or not a volcano erupts explosively is dependent on the composition of the magma. Gases are easily able to escape thin, runny magma, so when an eruption occurs, the lava spills out of the volcano like in eruptions of Hawaii's Kilauea. On the other hand, gases can become trapped in thick, sticky magmas. The pressure within the magma reservoir increases until the gases violently explode in eruptions like Washington's Mount St. Helens. But the hazards don't stop there. In explosive eruptions, ash is ejected into the atmosphere, where it can circulate and deposit vast distances from the volcano. Ash can be extremely harmful to aircraft by abrading parts of the outsides of planes and clogging essential parts of the engine. Ash can rain down from the sky, blanketing the environment with a layer thick enough to suffocate plants, animals, and people, and damaging infrastructure. If hot volcanic substances mix with water, ice, or snow melt, mud flows known as lahars can form, creating a fast-changing, hazardous scenario capable of destroying entire communities. Volcanoes need to be monitored so that warnings for hazards like mud flows and lava flows can be issued to surrounding communities. The United States Geological Survey operates 5 volcano observatories around the country, each devoted to volcano monitoring and research in specific geographic regions: Alaska, the Cascades, Yellowstone, California, and Hawaii. How do these observatories monitor volcano hazards, though? Volcano monitoring consists of a variety of methods, including earthquake detection, ground deformation measurements, rock and water chemistry, and volcanic gas analyses. All these measurements can be used to keep track of how a volcano's magma is moving beneath the surface. While volcanoes are complex systems that exhibit unpredictable behaviors, better understanding and modeling the physics behind volcanic eruptions and monitoring of volcanic trends and behaviors has allowed scientists to forecast volcanic eruptions with geodetic and seismic methods. Earthquakes happen all the time around volcanoes. This is because as magma rises to the surface, it disturbs the surrounding rock. The changes in stress distribution and pressure frequently cause fracturing, leading to small but detectable earthquakes. While normal magma movement will result in background seismic activity, earthquakes larger or more frequent than this background noise may be one of the first indicators of a potential eruption. These precursors are usually shallow, within 10 kilometers of the surface, small in magnitude, and can occur in swarms of dozens to hundreds of seismic events. Seismologists are also able to further constrain the type of volcanic activity based on the earthquake signal, specifically 3 different types of earthquakes. One is what scientists call volcano-tectonic earthquakes, which occur because of brittle failure of rock. These events can happen because of changing stresses as magma and fluids move through pre-existing cracks in the rock. These processes are complicated and usually need additional geodetic, geochemical, and hydrologic data to be fully understood. There are also long-period or low-frequency earthquakes. These are often detected prior to an eruption due to cracks in the rock resonating when magma and gas ascend. These earthquakes can also be part of normal background seismic activity and can be caused by non-magnetic processes such as glacial movement. Lastly is volcanic tremor. These high-amplitude signals can be caused by continuous volcanotectonic or long-period or low-frequency events, explosions, or enduring resonance from long-lived magma movement through cracks in the rock. For example, when Mount Redoubt in Alaska erupted in 1989 to 1990, warnings were issued in advance of the two explosions because of 11 swarms of precursor earthquakes. Geoscientists analyzed the long-period seismic activity and deduced these swarms to be from movement of high-pressure fluids traveling along fractures inside the volcano as the magma ascended to the surface. This precursor detection allowed advanced warnings to be issued prior to the volcano's explosive eruptions. Geodesy, the study of Earth's geometric shape and orientation, also helps us understand volcanic processes, such as eruption mechanisms or the internal plumbing system that magma may travel through. Geodetic data can be used to characterize times of volcanic unrest, leading to more accurate hazard assessments. Geoscientists can measure ground deformation for volcano forecasting. Ground deformation, caused by movement of magma through cracks and faults, can be measured earlier than other indicators, like seismic activity, which does not occur until a strain threshold is reached. Ground deformation can also be caused by other processes, like tectonic motion or geothermal activity, so it's important to measure how exactly the surface is changing. Ground inflation is often observed prior to eruption, as the magma has risen to the surface and is pressurized. GNSS and INSAR are both methods that are useful for ground deformation monitoring and help forecast volcanic eruptions. For example, Mount St. Helens developed a bulge on its north side in early 1980. By the end of March, the bulge was increasing in size by nearly 2 meters daily, exceeding 130 meters by May 17th. This helped scientists to understand that an eruption was imminent and likely going to happen from the north side, where the bulge was forming. Chemical analyses of volcanic gases can also be used to monitor when an eruption may be on the horizon. As magma rises, it depressurizes, much like a can of soda fizzes once the seal is cracked. This process releases specific types of gas, like carbon dioxide, sulfur dioxide, and water vapor. When detected by scientists at the surface, it can mean the volcano is becoming active. For example, high concentrations of sulfur dioxide gas at Mount Pinatubo in 1991 indicated that the ground deformation activity was not related to geothermal activity, but instead magmatic unrest. In early June 1991, there was a decrease in sulfur dioxide flux indicating that the volcano was sealing. This caused increased pressure and made the conditions ripe for an explosive eruption, the second largest in the 20th century, which then occurred on June 15th. Volcanoes are complex systems, and having a plethora of techniques at the ready to monitor their behavior is key to accurate and timely forecasting. Part of the formula is keeping the public aware and engaged with volcano hazards. Scientists are always looking to improve the ways we monitor and forecast volcanic eruptions. Every day, we make improvements with the integration of more sensitive instruments, ground-based and remote sensing techniques, and the flourishing of machine learning for data processing. With every step of progress made, we come closer to helping to keep people around the world informed and safe.